In the last rather long video, we discussed Hamilton's principle for discrete systems. We talked about the variational principle. We showed that the Euler equation for Hamilton's variational principle is Newton's second law, F equals ma. And now I want to do a series of 3 examples. The first 2 are really just high school physics examples that you could do easily using F equals ma, and you probably have before. But we're going to do them using Hamilton's principle. Obviously, we'll get the same equations of motion in the end. And then the third example is also relatively straightforward, but it illustrates one of the properties that I emphasized in the last video of Hamilton's principle, and that is that it is independent of the coordinate system. Unlike F equals ma, the choice of a coordinate system is actually a secondary consideration. We'll see that in our third example. So the first example is just 2-dimensional projectile motion. Very simple problem, but let's do this using Hamilton's principle. So we have an object of mass m, and it's being shot at an angle theta 0 from the origin in the xy plane. So it's just 2D projectile motion, and it has a velocity v0 at the time it's shot. And we want to determine the positions x and y as a function of t. So the dependent variable r of t is now going to be x of t and y of t. We have 2 dependent variables. It's a 2-degree of freedom system. We're going to keep things simple. For now, we'll neglect drag, so there's no friction, no non-conservative forces. So we have our initial conditions. X and y are at the origin at t is equal to 0, and the velocities in the x and y direction are given by v0 cosine theta 0 and v0 sine theta 0. So we have one particle, one rigid particle, so capital N is 1, and we have 2 Cartesian coordinate directions, x and y. So big N is 1, and little n is 2. Again, 2 degrees of freedom. So when we do these problems, the first step is to form the t and the v. In other words, to get the Lagrangian in Hamilton's principle. Once we get the Lagrangian, the rest of it's pretty much plug and chug to get the corresponding Euler equations. For now, we're not going to consider the fact that we may know the general form of the Euler equation. I'm going to take the variation of the functional, set it equal to 0. We'll do that for these 3 examples. We'll get tired of it pretty quickly. And then in a subsequent video, we'll look at the general form of the Euler equations for these particular situations. So we want to form the kinetic and potential energy functions. So v, the velocity, is the time rate of change of position r, and so that's v sub xi plus v sub y j, again in 2-dimensional Cartesian coordinates. Well, the velocity in the x direction, that's just dx dt, so that's just x dot I plus vy. The velocity in the y direction is y dot dy dt in the j direction. So then the kinetic energy of our projectile, in other words, 1/2 mv squared, or 1/2 m r dot dotted with r dot, is then just x dot I plus y dot j dotted with itself, which is x dot squared plus y dot squared. So it's a scalar. It's the sum of the squares of the components of the velocity. So 1/2 times m times the quantity x dot squared plus y dot squared. Now remember, we don't have any drag, so the only force acting on our projectile is that due to gravity. And so that's conservative, of course. So it's a conservative force, and it's 0I, gravity does not act in the x direction, minus mgj. So it's minus mg, mg is the magnitude, and it's in the negative y direction. So that is the conservative force vector corresponding to gravity. Now our 2D projectile is free to move in both x and y directions. So the virtual displacement, remember the virtual displacement are the directions that the object could move in. Maybe they do, maybe they don't, but it's the directions that they physically could given the geometric constraints. So our delta r, our virtual displacement, is delta xi plus delta yj. Remember, delta r is a vector. So delta r is a virtual displacement vector. So then our potential energy v, which is just the negative of the integral of f dot delta r, the f is our minus mgj, dotted with delta r, which is delta xi plus delta yj. So that's minus mg delta y. Now I'm going to put a y bar here. That's a dummy variable. So y bar goes from 0 to y to capture the motion from t1 to t2. We have the integral of mg with respect to y bar. mg is just a constant, so the integral of delta y bar is just y bar, and that goes from 0 to y. So the potential energy is just mgy. Now that's, of course, sounds familiar. That's the mass times acceleration due to gravity times the height, y. That's the total potential energy. So in fact, we never have to evaluate F dot delta R for gravity again, because we know as long as my y is up in the opposite direction as the gravity, the potential energy will be mgy. Okay, so we have T and we have V. So then the Lagrangian is T minus V. So that's the mass times the quantity 1/2 times the quantity x dot squared plus y dot squared minus g times y. That is L. So the rest of this now is basically plug and chug. I have the variation of the integral of L is equal to 0. In this particular case, L involves the independent variable t, the y position, the x velocity, and the y velocity. So I take the variation of L given these variables, and I have partial L partial y delta y plus partial L partial x dot delta x dot plus partial L partial y dot delta y dot. I've already taken into account that t is in fact our independent variable and therefore does not vary. So what's the variation of L with respect to y? Well, if we go back here, there's no y term here, there's no y term here, so it's minus mg. So partial of L with respect to y is just minus mg. M's out front here. Partial L partial x dot, no x dot here, no x dot here. We have a half m times x dot squared. So the partial derivative of this with respect to x dot is m times x dot. The twos cancel. Same thing for partial L partial y dot. That's just m times y dot. We want to get these derivatives off of the delta x and delta y. So we use integration by parts to do that, and that gives us a minus, don't forget the minus sign, x double dot times delta x, and minus y double dot delta y. Now you notice I didn't bother showing the terms at the endpoints from the integration by parts because those vanish. So now I can gather everything times delta x and everything times delta y, and those will give me my, in this case, two Euler equations. So times delta x, I have x double dot, and times delta y, I have y double dot plus g. So those are the two Euler equations that we get from Hamilton's principle. So if we integrate these twice and put in the initial conditions on position as well as velocity, then we get these two expressions here. And those are the same expressions that you get from high school physics when you applied Newton's second law, F equals ma. So let's look at a second example. This is the undamped harmonic oscillator. So we have a spring, a linear spring, spring constant K, connected to a frictionless mass M, which can go left and right. X of t will be measured from its neutral position. So when the spring is such that there's no force in the spring, that will correspond to x of t is equal to 0. This is a 1 degree of freedom system, even though we have two discrete pieces. There's the spring and the mass. But we only need one dependent variable. X is a function of t that tells us where this mass is. From that location, we can get the force in the spring and anything else we want about the system. So capital N is 2, but little n, number of degrees of freedom, is 1. Now a couple of assumptions we'll make. First of all, the spring itself we'll assume has no mass. Of course, that's never true, but we'll say it's small compared to this mass such that we can neglect the mass of the spring. So then the spring itself will only have potential energy and no kinetic energy. Then secondly, because this mass only moves horizontally, we're going to call that level the zero potential energy level. So no effect of gravity. It's just moving without friction back and forth. And so there's no potential energy of the mass, and there's no kinetic energy then of the spring because it doesn't have a mass. So then the total kinetic energy, T, is only due to the movement of the mass. That's 1/2 mv squared. The velocity of the mass is simply x dot. So it's the time rate of change of the x position. So 1/2 m x dot squared. V then is only due to the potential energy of the spring. That is due to the strain energy, which we denote by a capital U. Capital U is the strain energy of something that's deformable, such as a spring. So we have the strain energy, it's minus F dot delta R, and the F is minus k times x. So that's the restoring force of the spring, which is always the negative of the spring constant times the elongation of the spring, which is x. Delta r is just delta xi. It can only move in the x direction. The negatives cancel. K is a constant, bring that out front. So we integrate x bar with respect to x bar, again using a dummy variable here, just like we did for y. Integrate x with respect to x, and you get a half times k times x squared. Again, that'll sound familiar from high school physics. That is the strain energy or the potential energy of a spring that is either being elongated or being compressed. So now we can write down the Lagrangian, just t minus v. Again, that's just now t1 minus v1, so 1/2 mx dot squared minus 1/2 kx squared. So then we have the variation of the Lagrangian is equal to 0. That's Hamilton's principle for conservative force field. And L now is a function of t, independent variable, the dependent variable, which is the x position, and its first derivative. Again, because t is an independent variable, it doesn't vary. So taking the variation gives us partial L partial x delta x plus partial L partial x dot delta x dot, and that has to be equal to 0. So take partial L partial x, no x here, partial derivative of x squared with respect to x is 2 times x. So the 2 cancels with 1/2, so that's minus kx delta x. Same idea, partial L partial x dot. From this term, we get the mass times x dot times delta x dot. Then we use integration by parts to get the derivative off the delta x dot onto this x dot. And then we can write everything with no deltas in it times the variation of x, which is our dependent variable. And that integral is equal to 0, which again gives us the Euler equation, x double dot plus k over mx is equal to 0. That, of course, is the equation, the differential Euler equation that governs the motion of our undamped harmonic oscillator. Now, you might be getting tired of taking the variation of the integral of L less than equal to 0 every time, and that's fine, and we will get a more general form of the Euler-Lagrange equations for these problems based on Hamilton's principle in a later video. Okay, so this is a second order constant coefficient homogeneous equation. We know how to solve that, and we get this as the general solution. Now, I didn't give any initial conditions, so we can't get the C1 and C2 constants of integration, but we get sines and cosines of the square root of k over m times t. All right, let's do one more example, and in this case, we're going to emphasize this fact that Hamilton's principle is independent of the coordinate system. And so the choice of the coordinate system will actually be a secondary consideration rather than a primary consideration. So we first focus on getting the t and the v, the kinetic and potential energy for the system. We'll write them down in their most natural variables, and then we'll later determine what variable or variables we want to use in order to express this system in a particular coordinate system. So we have a mass m hanging from a massless rod of length L from the origin here. And this is rotating around the vertical y-axis with a angular velocity theta dot, which will be capital omega. So that's a constant value, and that's the rate of rotation of the mass around the y-axis. We'll have an angle alpha from the vertical, and we'll also have a radial distance r out from that center axis of rotation. G, of course, will be down. We want to determine this angle. We want to determine alpha. Okay, so let's just talk about the physics of this a little bit. So the location of the mass, we need to think about how many degrees of freedom, how many variables do we need to fix the state of the system. It turns out that the location of mass does not depend on theta. In other words, the azimuthal angle does not affect the forces or anything about the system. And so we say that it is axisymmetric. The kinetic and the potential energies are independent of theta due to this axisymmetric character of the rotational aspect of our problem. Now, in terms of variables, we could use the radial distance r as our variable. We could use the elevation y. We could use the angle itself, alpha, which is what we're looking for. But the point here is I don't have to decide that now. I don't have to determine what my dependent variable is going to be. I can let that for a later decision. So we have one particle, capital N is 1, that's our mass, and 1 degree of freedom, because all I need to know is either alpha, y, or r, and I will know the state of the system. Okay, so let's write down the kinetic energy, and I'm going to do so using the most natural coordinates that I can, given the rotational aspect of this system. So my 1/2 mv squared, the v, will have a vr component, a v theta component, and a vy component in cylindrical coordinates. But there is no radial velocity, because it's the same angle. There is no y velocity, it's not moving up or down. There's only a v theta, that azimuthal velocity. So we have 1/2 times m times v theta squared. V theta squared, well, that's just r times theta dot, the radial distance times the angular velocity theta dot, and theta dot is capital omega. So it's 1/2 times m times the square of omega times r. Now I've highlighted the r in red here for reasons you'll see in a moment. Then for the potential energy, well, the potential energy is only that due to gravity. We've already done that calculation in our first of the 3 examples, so that's just mgy. So again, just be sure that y is positive up, so that the gravity is in the opposite direction, and in that case, then the potential energy is plus mg times y. Again, I'm just writing each of these in the most natural form, the most natural variables possible. For this one, it happens to be r. For this one, it happens to be y. Okay, so then we form the Lagrangian. Lagrangian is t minus v, so it's 1/2 times m times the square of omega times r minus mgy. Now again, for my single dependent variable, I can use alpha, r, or y. Now you notice alpha hasn't appeared in either of these yet, so there's no point in using alpha, although I could. Instead, I'm going to use y. So I'm going to keep this y here, and then the r, purely from the geometry, r squared is l squared minus y squared. It's just a triangle. So now I've written my L in terms of my one single dependent variable, in this case, the vertical location y. This is somewhat arbitrary. I'm just recognizing the fact that it's a 1 degree of freedom system, so I want to simplify my Lagrangian to take that into account, but it could be any one of these 3 variables. So I've written my Lagrangian solely in terms of y in this case. But again, you can see that was a secondary consideration. And this again emphasizes the independence on the coordinate system. It's not that we don't have a coordinate system, it's just that Hamilton's principle itself is not dependent on that coordinate system. So I take the variation of the integral of L and set it equal to 0. In this case, L is only a function of t and y, so that's partial L, partial y, delta y, partial L, partial y. I have a y here and a y here. I take the partial derivatives. I will get minus m times cap omega squared times y, and then minus m times g, all times delta y. You'll notice I don't have a y dot because there is no velocity y dot. So in fact, my Euler equation here, the equation of motion, is really just an algebraic equation. Normally it would be a differential equation. In this case, the value of y is a constant. It doesn't change with time, so we get an algebraic equation for y instead of a differential equation in this particular case. So we were asked for alpha, so from the geometry, minus y is equal to L cosine alpha. Remember, y was positive up, it was hanging down from the origin, so y is always negative, so minus y is L cosine alpha. So if you solve for alpha, that's the inverse cosine of g over L times omega squared. You'll notice one thing's missing, the mass. So the alpha angle does not depend on the mass. Some additional comments. First of all, again, just emphasize, there is no special consideration that was given to the fact that we use cylindrical coordinates. So that was, again, a secondary consideration, not a primary one. It was also not necessary to determine the force in the massless rod. If you were to do this problem using F equals ma, you would write a free body diagram for the mass, and you would have to replace the massless rod with the force in the rod. And you'd have to figure out what that is in order to apply F equals ma to that free body diagram. That was not necessary here in the context of Hamilton's principle. Now just to remind you, this is rather unusual. The equation of motion is almost always a differential equation. It's very rarely that it's an algebraic equation, as was the case here. So don't expect to see that in the future.